Good morning, everyone. I'm Ivy Caro Lomerio, and this morning I will be presenting some of the results of our work entitled Asymptotic Analysis of a Certain Class of Semilinear Parabolic Problem with Interfacial Contact Resistance. This is actually part of my master's thesis, and Dr. Edita Jose is my advisor. And we're from the Philippines. Okay, so here in this problem, we consider a time-dependent semilinear parabolic problem with interfacial contact resistance. So our main goal is first to prove the existence and uniqueness of the weak solution of the problem, and then we use the periodic unfolding method to get the homogenization results. Okay, so this is our domain. So we've seen this a couple of times already. So here we have our domain omega, which is a bounded open subset of Rn. The boundary of omega is denoted by partial of omega. The two components are omega 1 epsilon and omega 2 epsilon. So omega 1 epsilon is the yellow part, and then the green part is omega 2 epsilon, which is periodically distributed throughout the domain. The red part is the boundary of our second component, omega 2 epsilon, and we call it the interface, and we denote it by gamma epsilon. And then from here, we choose a reference cell, Y. So this is Y. The first component will be Y1, the second component is Y2, and the interface is gamma. And then we introduce two new sets. So here, gamma epsilon hat is the union of all the cells that do not intersect the boundary. And then lambda epsilon is omega minus omega hat epsilon. Okay? So we use this functional spaces. We've seen this, right? A lot of times. So we have V epsilon, which is the set of all V1 in H1 omega 1 epsilon, such that V1 is 0 on the boundary with this norm. Okay, and then H epsilon gamma, is the set of all couples V1, V2, such that V1 is in V epsilon and V2 is in H1 omega 2 epsilon with this corresponding norm. Okay, so these are our assumptions. So we have the coefficient matrix A. It is an n by n symmetric Y periodic matrix valued function in L infinity of Y, such that for all n tuples, we have this, okay? And then we define A epsilon of x as A of x over epsilon. And then we also have a Y periodic function H, which is in L infinity, okay? And such that H epsilon of x is H of x over epsilon. Okay, so some more assumptions on our data. So we want U epsilon, U0 of epsilon to be U01 epsilon, U02 epsilon from L2 omega 1 epsilon cross L2 omega 2 epsilon. And we want our F to be a globally Lipschitz continuous. Moreover, for each pair U and V from L2 omega, so we want the function omega defined by this to satisfy the following properties. So we call this the measurability property. So later you will see why we have this additional assumption. Okay? So this is our epsilon problem. For t greater than 0 and gamma less than 1. So we have this, the parabolic problem. U1 epsilon and U2 epsilon describes the temperature on omega 1 epsilon and omega 2 epsilon. The first two equations describes the heat diffusion in the components. The third equation describes that the normal component of the temperature field is continuous, and it is proportional to the flux of order epsilon raised to gamma. And then we have here our boundary condition and then the initial conditions. Okay, so for the linear case, this problem was studied already by Dr. Jose using the same domain. And then the elliptic and the wave problems are, I think, studied by Dr. Donato and Sarah Monsoro. Okay, so this is the variational formulation of our problem. So it's almost just the same, except that it has two components. And as you can see, on the right-hand side, we have this. So we have our f. By the way, this means that the right-hand side, since it is f of u1 epsilon, it means that the source of the heat is dependent on the current temperature of each point on the domain. So this makes it semilinear. Okay, so this is our W epsilon. And then this is the norm in W epsilon. Okay, so for the existence results, what makes it a little difficult is the presence of the semilinear term because we're not able to apply the Galerkin method. And so we found this theorem by Zeidler. So if you, it states that if you have here a semilinear problem, and then you assume that A is a linear operator that is self-adjoint and semi-bounded. And then A plus AI is strongly monotone. And that this is true. It's like the Lipschitz condition. Then this problem will have a mild solution. Exactly one mild solution. But we wanted the weak solution. And so, so again, this theorem states that our semilinear problem has exactly one mild solution, but we want the weak solution.
Because you said linear.
Sir?
You said it is linear growth, right?
Yes. Okay, so and then we use the following theorem by Showalter. It states that suppose the H1 through H3 hold, and then with this additional assumption, which is our measurability condition, then the mild solution is exactly the weak solution of our semilinear problem. So with this, we just define an inner product on H epsilon gamma. So we have this, and then we prove that this operator satisfies H1 through H3, so it is linear, self-adjoint, semi-bounded, and strongly monotone. And then since F is Lipschitz continuous, and so using the theorem by Zeidler, we prove that our problem has exactly one mild solution. And then again, by the measurability condition, we proved by the theorem of Showalter that the mild solution is the weak solution. Okay, and then for the a priori estimate, so in order to get uniform estimates and homogenization results, so we impose this assumption that the extension of U0 epsilon converges weakly to U0, which is this, in L2 omega cross L2 omega for I equal to 1 and 2. And then we have the following estimates. Actually, this is the same for all the parabolic cases. Okay, so the proof of this just follows from Dr. Jose's paper. Okay, and again, I mentioned earlier that the homogenization results were derived from the periodic unfolding method. The difference from what Dr. Onofrei introduced to us is that in this definition, we have the variable t because we are considering a time-dependent problem. But it's just the same. We just added the time component. Okay, so this definition and all the other results that I used came from Zhanying Yang's paper. He studied actually almost the same. A parabolic problem with interfacial contact resistance, but his case is the linear case. So again, Ti epsilon of V is equal to this. okay, with the time component t, inside this space, and then 0 outside. And so these are the homogenization results. We have 3 cases because if you can remember the problem, you have epsilon raised to gamma. And then it was proved by Hamel that the solution is not bounded for gamma greater than 1. Okay, and then so we only have the values for gamma which are negative infinity to 1, equal to 1. And so since there will be different limit problems that will arise from the values of gamma from that interval, we have 3 cases. So the first case is for gamma from negative infinity to negative 1, and then gamma equals negative 1, and then gamma from negative 1 to 1. We were not able to prove the case where gamma is equal to 1. So this is the homogenization results. So we have A epsilon and H epsilon as defined before. So for gamma less than negative 1, suppose that U epsilon is a solution to our problem, so our epsilon problem. Then we have U1 in this space, and U1 hat in this space, and U2 hat in this space, such that these convergences hold. As you can see, T1 epsilon of U1 epsilon converges weakly to U1, and also the same is true for T2 epsilon, U2 epsilon. It's because it was proved by Yang that for gamma less than negative 1, U1 epsilon is just U2 epsilon. So it's just the same. Okay, so here the pair U1 epsilon, U1 U hat is the unique solution of this problem. Okay, and such that U hat is the extension by periodicity of this function. It's not really nice to look at. Okay, so the main difference with Yang is that this right-hand side. So here it's just the integral from 0 to t, the integral over omega of f, and then this psi phi dx dt. But here we have f of u1 plus f of u2. Okay, so, and then we have this. U hat is equal to this, and it is the solution of the following cell problem. And U1 is the solution of this. So again, we have here U1 and U hat. So this is U hat, which is the solution of this, and U1 is the solution of this homogenized problem. Okay, so again, the proof of this theorem is almost the same as the proof of Yang, except for the right-hand side. So the assumption on F, which is F is globally Lipschitz continuous, makes it easier because T1 epsilon of F, U1 epsilon will just be F of T1 epsilon, U1 epsilon. Okay, and then we have, for the case of gamma equal to 1, we have the same convergences as before. Okay, but this time, where is U2 hat? Sorry. So this time, this triple is the solution of this. That was 20 minutes. Sorry. Okay. Okay. So again, for the case gamma equals -1, the difference from the proof of the previous theorem is the presence of the interface term, because it did not disappear. In the previous case, it disappeared. So here we have epsilon raised to -1. Yes. And then we also have the case for gamma in -1 to 1. Actually, Yang's work is just for the case gamma in -infinity to -1, including -1. So here, the proof of this theorem, we did it on our own, but we followed the proof of Tarju. Prof. Donato, Linguyen, and Tarju. And so the difference is, but his case is the elliptic case and linear. And the difference with the other theorems is that here, T to epsilon of the gradient of U to epsilon converges weakly to 0. Okay, so we also actually have the corrector results for this, but I did not present it because the time will not be sufficient. But if you want the details, so this can be found in the Bulletin of Malaysian Mathematical Sciences Society. So, maraming salamat. Thank you very much. I would like also thank Professor Donato for providing us with this problem and her insights. And thank you for the organizers for allowing us to be part of this business meeting. Thank you very much.